Welcome to the second unit of the fifth week in the Parallel Programming Concept course. After we had a look into how shared nothing systems look like and how clusters and supercomputers are built today, we next want to go into the question of how you can parallelize a particular problem in the best possible way for a particular hardware environment in the shared nothing world. So in week number 4 with Frank Feinbuber, you already saw that you can make a basic distinguishing between task parallel and data parallel problems. In a task parallel problem, we take our parallel application and we define different tasks with a different purpose, with different work to do. And at the end, we aggregate the result of the different parallel tasks in order to get an overall application result. In data parallelism, we have the same kind of instructions or algorithm being applied to different slices and parts of the input data set. So we basically divide our input data into separate tasks and then at the end take all the partial results, collect them again in order to formulate an overall application result. So with the notion of task parallelism and data parallelism in workloads, we also saw in the last week that the question of granularity of task size, how big you choose just a chunk, this is flexible. This can be defined by the application developer. So you as a developer has a choice to say, do I want to do a very fine-grained decomposition of my problem with very small tasks so that I have a lot of them? This is a very good approach for GPUs and graphic cards. Or do I want to have a more coarse-grained approach where I have big chunks of data and only a few tasks? What is the right level? And this is something that may not be that important in a shared memory system. For example, when you use OpenMP and you do your loop parallelization, it's not really relevant if you have very fine-grained or only fine-grained tasks. The work-stealing approaches inside the OpenMP runtime will manage that for you, so you will more or less get out with the same performance. In a shared nothing environment, the task granularity is a crucial issue because if you have more tasks, more fine-grained tasks, then you end up with more communication. And as we saw, communication is the major pain point in a parallel shared nothing application. So the interesting question here is, how do we deal with that problem? How can we consider the relevant overhead we get from the communication when we think about the granularity of our parallelization approach? And in order to rank this, there's a very helpful thought model which is called the surface to volume effect. The idea here is that you take your particular problem you want to parallelize, whatever it is, processing data, solving a computational problem, and you visualize this problem as a three-dimensional cube. The idea here is not to express your data in 3 dimensions inside your program, but just to take this as an envisioning, as a kind of visualization for your problem. So you take your problem and you visualize it for yourself as a 3-dimensional cube, and then you think about the parallelization as a slicing of this cube into tinier cubes. Yes, you make your problem, you slice up your big problem into smaller parts. And the question is now, how big do you make these chunks? How large do you do the slicing? And the idea here is that you say your cube slices have a particular volume depending on your choice of granularity. And this volume is an expression for the computational work. So if the overall big cube is your overall work you have to do, then the parallelization basically leads to tinier cubes. And each task now is equivalent to a particular cube slice. And the volume of this cube slice is then the expression of the computational work you put into a single task. The communication requirements are expressed by the surface of your cube slice. So the surface, all the area around the cube, this is where you potentially need communication with the other tasks in order to exchange intermediate results or other data, or maybe even just if you want to do synchronization, for example, with a barrier. So the idea is that you take the surface of your cube slice and the volume and you put this into relation, and then you end up with something which is also called in the literature the communication to computation ratio. So you take a particular task granularity, a particular size, and then you set the communication and the computation that results from this per task into relation. So if you have a fine granularity, then you get a comparatively high communication work that has to be done because your cube is very tiny, you had a lot of them, so you have more computation between all these different tasks. And you have a low computational amount of work per task, per cube slice. If you take a more coarse-grained granularity, then it's the opposite. You have a low communication overhead and you have a high amount of work per cube. And the interesting question is now, if you take this thought model, what is the better way? And the trade-off you have to do in this situation is that you either want to do a fine-grained decomposition in order to use all the processing elements available, or you want to do a more coarse-grained parallelization in order to reduce the communication overhead. So if you just make your granularity more coarse and you have not very huge tasks, then you may end up in a situation that you don't use all the available processing elements, all the available machines or processors or cores. So the point is, a coarse granularity is good to avoid communication overhead, but there's a limit in this. And for each and every application and the according execution environment, you have to find the right balance. So considering the surface to volume effect is basically a design decision that you have to make when you target a particular platform with a particular application. So this has to be rethought each and every time you either move to a new platform or you tackle a new application problem in your parallelization attempt. Here's an example from Ian Foster, who was one of the authors introducing this concept. So in his example, he used something that we know as the heat map example. We introduced heat map as a coding exercise for you in week 3. The idea here was that you have different cells, and these cells have their temperature, and then they exchange that temperature information with the neighbor cells and update their own value according to a heat spreading scenario. And when you take a heat map example and you take 64 data cells to be simulated in your parallel simulation, then you have two choices when it comes down to granularity. You may want to say, okay, I define a single parallel task in my overall application for each and every of these 64 cells. This is version number A in the picture here. If you do this, you end up with 256 messages being exchanged and with 256 data values. So this is a lot of communication on the one hand, but on the other hand, you are able to use 64 processing elements, for example, cores, in parallel. The other approach, the more coarse-grained approach, would be to use only 4 tasks and to have multiple data cells of your simulation being simulated on one of the tasks. So this leads to less messages, only 16, and also to less data values being exchanged, because some of the data exchange simply happens by shared memory interaction inside the task. The advantage, therefore, is that you get less communication, but the problem is that you only have 4 tasks now. So if you have 4 processing elements and not more, that's fine. But if you have more processing elements, you lose the possibility of leveraging them for increased speedup. So the balancing act really is to partition your problem in a way that it fits to the particular environment. And this means that if you do some kind of software development, it is better to not statically partition your problem in the parallelization, but to make this configurable. So it is always a good strategy to do parallelization on a level where you have some knobs to tweak, some configuration that allow you to define the granularity. An even better approach is if your software inspects the execution environment and determines by itself what the best granularity is for this and that particular computational environment. So the rule of thumb with the surface to volume effect that we would like to recommend to you is that if you target a shared nothing environment, then the situation in practice is that you typically have a cluster, and each of the cluster nodes has multiple cores. So you have a bunch of shared memory systems, parallel shared memory systems, interconnected by some network. So you get out with something like a hybrid of shared memory systems being put together as a bigger shared nothing system. And if you now consider the surface to volume effect, then the idea is that you take your parallel problem, you slice it up into tasks, and then you agglomerate your tasks and you build coarser grained parallelism until you have the limit of exploitation for your processing elements. So you do a coarse grained granularity down to a level where you're still able to use all the available processing elements in your infrastructure. It is also a good idea to agglomerate in all dimensions. So if you have three-dimensional data structures, for example, don't try to optimize your problem in a way that you agglomerate the task only on one level, but try to do this in all dimensions at the same time. The influencing factors you have to consider here are the communication technology and the topology of your interconnection network, the speed of your single node, so what is the serial performance per processing element, how much do you get by putting multiple data items into one single task, and the degree of application parallelism. Maybe you are simply not able to do an arbitrary kind of parallel task, but there are some limits inside your application design. The task communication graph you get from your parallelization attempt and the network topology, they must map on each other. This is known in research as the task mapping problem. So you have a task graph, a couple of tasks communicating with each other, and you have your interconnect technology, and somehow you now must map this application task graph onto the execution environment. And this is something that is an unsolved problem. So the idea of having a generic solution here is not feasible. This is a graph mapping problem, and there's still research going on. Today, if people need to map their shared nothing applications at their task graph, where the tasks communicate with each other, to a particular environment, this is basically manual optimization. So you start with a first round, you place your application on an execution environment, you see how it acts, where the bottlenecks are, and then you try to rearrange your tasks in a way that the communication infrastructure, for example a fat tree, is leveraged in a better way. So this is an interesting topic, not only in practice but also in research. There are some fascinating trends, for example, in the supercomputing world, where people now work on configurable networks, where you are able to reconfigure the interconnection network at runtime in order to adopt the particular hardware installation or the network installation to the workload you get in this moment. So there are interesting ideas here. We will recommend you some readings on the according recommended readings page.